All right. So this is 5-1, bisectors in triangles. So it's the different types of bisectors. And we have done isosceles triangles. And if you remember, I said an isosceles triangle has the vertex angle is bisected by a perpendicular bisector. This is, again, basically an isosceles triangle without the constraint of it actually being a triangle. So if a point is on the perpendicular bisector of a segment, all right, so perpendicular bisector is going to be yellow. And I know it's this line because of the 90-degree angle. That's how I know this is the perpendicular bisector. And because it's cutting the segment into two equal parts. So I can see this has one line and this has one line. So it's two equal parts, so it's equidistant. Oh. If a point is on the perpendicular bisector of a segment. So the point on the perpendicular bisector is point P. It is on the perpendicular bisector. Perpendicular bisector I know because it has the 90-degree angle. And it's cutting this segment into two equal pieces. So this point is equidistant from each of the endpoints of the segment because it meets the segment at 90 degrees. And it's exactly in the middle. What that's saying is that this distance, let's not pretend that's a straight line, is going to be congruent to this distance. So A to P is going to be the same as B to P because of the perpendicular bisector theorem, and you see how it creates an isosceles triangle.
Is P upside down at the top?
Right here? No?
Oh. I couldn't see P.
And then the converse, I know every time we do a theorem, we do its converse. It just means the same thing in the opposite order. So this is saying that if a point is equidistant from the endpoints of a segment, so here's the point P again, and it's equidistant from the endpoints A and B, so this side is the same as this side, then we can conclude that it is also on the perpendicular bisector, even though it's not drawn. Of this, M is the perpendicular bisector of AB, segment AB. So we can draw this line, here it's called M, line M. Because you have a segment and this point is equidistant from the two endpoints, that means you can draw a line perpendicular to the segment and it will split the segment into two equal pieces. So based on those two theorems, or that theorem and its converse, if line CD is the perpendicular bisector of segment AB. All right, so let's look at it. Think about what it's telling us, one little piece at a time. CD is the perpendicular bisector of segment AB. Find CA and DB. Okay, so CA from C to A. Well, if this segment has been bisected with a perpendicular bisector, that point C at the top is equal distance to B as it is to A. So if the distance to B is 5, the distance to A is also 5. So those are the same. So CA must be 5. And if we look at the bottom half, so the same situation is happening, but down here, we find DB. We have line CD is the perpendicular bisector. So point D is equal distance to A as it is to B. So B must be 6. Based on the relationships of the perpendicular bisectors. 90 degrees is very important, and the fact that it's bisected, or going the other way around, the distance from a point to the endpoints, if they're the same, and you have 90 degrees, then you know the segment's been bisected. All right, so find the length of segment AD. All right, where is A and D? So we're looking from A to D. This is what we want to find, is that length. Well, let's see, what do we have? Do we have a perpendicular bisector? Well, I see 90 degrees. And it looks like this, if this is the bisector, BD, then you could say that segment AC is cut into 2 equal pieces, so it has been bisected. So that means that yes, BD is a perpendicular bisector of AC. And then we can conclude that if the segment has been bisected, that the distance from A to D on one side is the same as it is on the other side. All right, that doesn't solve the problem right away, but we can see if this side is the same as this side, and we have an expression for each of them, we would write that as an equation. 11y plus 3 is equal to 6y plus 18, because AD is congruent to CD. And now that we have an equation, we can solve it. To solve it, we want the y's to one side and the non-y's to the other. So we're going to start with subtracting the 6y to get it on the left. So 5y plus 3 equals 18. And then we can subtract 3. So 5y equals 15. And divide by 5. So y equals 3. But we're not asked to find y, right? We're asked to find the length of AD. And AD, we can see, equals 11y plus 3. So if we take the fact that y is 3 and we plug it in right there for y, then we have 11 times 3 plus 3. So that's 33 plus 3, which is 36. So segment AD is 36. So this one over here is 36. And if that's 36, the other one has to be 36 as well. Even though it didn't ask us that, I still labeled it. Next it says to find the length of AC. On something like this, you need to be careful whenever you're trying to find the segment length. What's wrong?
I looked away for 3 seconds and you get an answer. It's okay. Continue.
Okay, so find the length of AC. AC is the segment that I have highlighted yellow. Whenever you're solving for the segment side, be careful on, is it asking you to find half of it or all of it? In this case, it says A to C, AC, so it's the entire thing. It's both pieces. But we start off by just saying that they equal each other, because that's all we can do, is that we have this side with one line, AB is congruent to CB, so that means that 7x equals 5x plus 12. So those two pieces are equal, and so we can solve by subtracting 5x. So 2x equals 12, and divide by 2. So x equals 6. So we've solved for x, but this says to find the length of AC. So we could plug this in to either side and then double it, right? So if I want to find, I could find the length of AB. AB equals 7x. And if I know that x is 6, I can take it and plug it in for x. So it's 7 times 6, which is 42. And this is where I'm saying be careful, because the answer is not 42, okay? This piece that I marked as the 7x, that's 42, side AB. So we also know that CB is congruent, so CB is also 42. So the length of AC is going to be the 42 plus the other 42, so it is 84. So when you're solving on the segment end, be careful. Are you looking for half of it or all of it? The questions may differ. So we're okay with that? Okay. All right, so then that was segment bisectors, perpendicular bisectors. The other part is the angle bisector. Again, this is not something new. We've been over angle bisectors. It cuts an angle into two equal pieces. The wording here, it's one of those things, if you just read through it, it really doesn't make any sense. The distance from a point to a line is the length of the perpendicular segment from the point to the line. Doesn't make a lot of sense, does it? But if we look at the picture, and I'll try to explain it. So the distance from a point to a line. It's more like the shortest distance between two places is a straight line, that concept. That's kind of what it's saying, is if you have point D here, there's the point, and the line is like AC, which is a ray, but it's fine. I can't do these. Drawing on this board is hard. All right, so from the distance from a point to a line, from this point to this line, is the length of the perpendicular segment from the point to the line. So this dashed line, because that is perpendicular to the red line. Is this dashed line? That's the shortest distance between the point and the line. And you know that because of the 90 degrees. I mean, I could draw other lines to connect them, right? Because if I could do a line going like this, but that line's longer than this perpendicular line. Or from the point going this way, but again, that line is longer. So the best represent, like, how far away is that line from the point? How far away is this classroom from the Marbella fence across the way over there? Well, we need to go to the Marbella fence, do a 90-degree angle, and then measure it to my classroom.
Pretty far away, actually.
No, yeah, I know. But it's a good analogy, because that's what I see out the window. So it's not from here to anywhere on the fence. It's from here to the point that meets at 90 degrees. So you want to find the line that makes 90 degrees with the whatever line you're talking about, and that will line up with the point. That's the line that you want. That's the distance you want, not these other ones. So this is D. D for distance. That's the distance between the point and the line. All right, so the angle bisector theorem tells you if a point is on the bisector of an angle, then the point is equidistant from the sides of the angle. Same thing again, because you notice that the picture is very similar. This just has an extra requirement talking about the angle being bisected, because it says that OD, ray OD bisects angle AOB. So AOB, it's bisected, so it's cut exactly in half. So these two angles are the same, they're equal. And if a point is on the bisector of the angle, so OD is the bisector of the angle, then the point is equidistant from the sides of that angle. And to find that equidistance, you want the dashed line, the one that you'd be drawing, to be perpendicular to the sides of the angle. And that distance is going to be the same. So here, if this is at 90 degrees, and this is at 90 degrees, then this matches this. So dx is going to be congruent to db, or dz, segment dz. And then we have the converse, because we always have a converse. So on the first situation, the original theorem, you have the fact that the angle has been bisected. You know that the angles are congruent. And you conclude that the segments are congruent. In the converse, you have that the segments are congruent, and you're going to conclude that the angles are congruent. All right, so you're given that the segments are congruent, so we're going to conclude that the angles the angle has been bisected. So because dx is congruent to dz, ray OD bisects angle AOB. All right, so then we're going to do two examples for this. Find the value of x. Always pay attention to what you're solving for. I don't need to plug it in to find any distances. I just want to find x. I'm given the fact that the angle has been bisected. I'm going to change that up here in the notes. Because I'm given this. When you're given that the angle is bisected, that you know the distance between the point and the sides of the angle are congruent. So that's what we're going to apply here. We're given that the angle has been bisected. So we're going to apply the fact that these pieces are congruent because the angle has been bisected. So 5x equals 2x plus 24. Subtract the 2x. So 3x equals 24. Divide by 3. So x equals 8. And that's all it told me to do, is find out the value of x. If I wanted to find the length of the segments, I could. And I only have to do it for one. From B to F is 5x, so that's 5 times 8, which is 40. So if that side is 40, I don't even have to plug it into the other one, it's also 40. So I know both of these segments have a length of 40 something. Don't know the units. All right, that's when you're given the angles are congruent. In example 2, you're not given that the angles are congruent, but you are given that the segment, the distance between the point and the sides of the angle are congruent. And even though it's not going to ask us about that, oh yeah, it does. So here, since we know that these sides are congruent, these segments are congruent, then FD is congruent to FB. Or asked, what is FB congruent to? Well, FB is congruent to FD. And since FD is 10, that's actually what it's asking, isn't it? Then this side also has to be 10. According to the diagram, what can you conclude about CF? Segment CF. The ray CF. Because the segments are marked congruent, we can conclude that CF is an angle bisector. So we're going to conclude that CF is an angle, or ray CF bisects angle BCD ACE. All right, because these pieces were marked congruent and we see it goes through the angle C, it bisects angle C. So that's our conclusion, that CF bisects angle ACE, or that CF is an angle bisector of angle ACE. So since we've concluded that it's a bisector, I'm going to mark it as being congruent to each piece being congruent. They each have one line. And then it says to find x. So to solve for x, I see there's 2x and x plus 20. So 2x equals x plus 20. This one's actually pretty easy to solve for. I'm just going to subtract x. So x equals 20. All right, so if x is 20, we want the measure of angle ACE, A to C to E. Let me mark it in green. And it's made up of those two angles that are congruent, and we've already solved for x. X is 20. I really just need to solve for one of them. This is 2x, so 2 times 20, that's 40. And if the top one is 40, then the bottom one is also 40. Or you could solve it. X plus 20 is 20 plus 20. That's 40. 40 and 40 is 80. So this is 80 degrees. I'm going to write it anyway. The measure of angle ACE equals 40 plus 40, which is 80. And that's what this 5-1 bisectors of angles is about.